Hello. Today we're going to understand titration curves and pH calculation. Titration is a fundamental technique in chemistry used to determine the concentration of unknown solution by reacting it with a solution of known concentration. The titration curve graphically represents the change in pH as the titrant is added. And today I'll explain the titration curves for a strong acid, strong base, weak acid, strong base, and a weak base, strong acid. And followed by a step-by-step pH calculation for a weak acid, strong base titration. Alright, let's begin. In explaining the different graphs, we have the first one, which is a strong acid, strong base, and that could be, in this case, hydrochloric acid and sodium hydroxide. And so you see the pH starts very low, like around 1, and due to complete dissociation of the strong acid, that's why it's around 1. And the equivalence point occurs at pH 7, since the only species in solution are water and neutral salt. And the curve exhibits a sharp and steep rise in pH near the equivalence point. Alright, next. We have the weak acid, strong base, which could be acetic acid and sodium hydroxide. Alright, so the initial pH is higher, which is around like 3.5, because weak acids only partially ionize, and a buffer region is observed before the equivalence point due to formation of the conjugate base, and the equivalence point occurs at a pH above 7. It's typically around like 8.8 due to the basic nature of the conjugate base. The pH increase near equivalence is less steep compared to strong acid and strong base titration. Alright, and for the last one, we have the strong acid and weak base, which could be hydrochloric acid and ammonia. And so you see that the initial pH is low due to presence of a strong acid, and a buffering region is present as the weak base reacts to form a conjugate acid. And then the equivalence point is below pH 7, usually around like maybe like 5.5, since the conjugate acid form is weakly acidic. The pH change near the equivalence point is gradual, making the curve less steep than a strong acid, strong base titrations. Alright, as for pH calculations for weak acid and strong base titration, today we will calculate the pH at various stages of titration for 0.1 molarity of acetic acid, and then titrated with 0.1 molarity of sodium hydroxide, given that the Ka is 1.75 times 10 to the negative 5th power. Alright, starting for this, for a weak acid, it's calculated that the concentration is square root of Ka times the concentration of the acid, and so and also include the pH, which equals negative log of the concentration of hydrogens. Alright, so now we just substitute the values that were given. We got the Ka right here, and we're also given the concentration of the acid, 0.1. Alright, let's put this in. Alright. And this would give you something around 1.32 times 10 to the negative 3rd. And the pH, after plugging it into the negative log, you take this value, put in there, and this would give you pH equals 2.88. Alright, next, the calculation of Kb for the conjugate base. Alright, so we know that Ka KB times Ka equals Kw, but we're given the we know Kw is 1.0 times 10 to the negative 14 divided by 1.75 times 10 to the negative 5, which equals 5.71 times 10 to the negative 10. Alright, and then that gives us the KB value. Next, we can do the equivalence point pH calculation. So now that we have KB, we can input it and put the concentration of the acid in. So OH equals, while substituting the values, will be 5.71 times 10 to the negative 10 times 0.05, which equals 5.34 times 10 to the negative 6. And then if you know pOH equals negative log of this number, then you would get 5.7. And so if you do 14 minus 5.27, it equals 8.73, giving us the pH equals 8.73. Alright.